2.1 Agenticness, Agentic AI Systems and Agents. Agentic AI systems are characterized by the ability to take actions which consistently contribute towards achieving goals over an extended period of time without their behavior having been specified in advance. In the cultural imagination, an AI agent is a helper that accomplishes arbitrary tasks for its user, like Samantha from Her or HAL 9000 from 2001: A Space Odyssey. Such agents are very different from current AI systems like GPT-4, which, while surprisingly knowledgeable and clever in some ways, can thus far only complete a limited range of real-world tasks. Yet there is no clear line along which to draw a binary distinction between agents and current AI systems like GPT-4. Instead, an AI system's agenticness is best understood as involving multiple dimensions, along each of which we expect the field to continue to progress. We define the degree of agenticness in a system as the degree to which a system can adaptably achieve complex goals in complex environments with limited direct supervision. Agenticness, as defined here, thus breaks down into several components. Goal complexity. How challenging would the AI system's goal be for a human to achieve, and how wide of a range of goals could the system achieve? Properties of the goal may include target levels of reliability, speed, and safety. Example: an AI system that can correctly answer users' analytical questions across programming and law would have greater goal complexity than a text classifier that can only classify the same inputs as belonging to law or programming. Environmental complexity. How complex are the environments under which a system can achieve the goal? E.g., to what extent are they cross-domain, multi-stakeholder, require operating over long time horizons, and/or involve the use of multiple external tools? Example: an AI system that can play any board game expertly has greater environment complexity than an AI system that can only play chess, because the first system can succeed under a far greater range of environments, including chess, than the second. Adaptability. How well can the system adapt and react to novel or unexpected circumstances? Example: automated rule-based customer service systems have lower adaptability than human customer service representatives, since humans can address unexpected or unprecedented customer requests. Independent execution. To what extent can the system reliably achieve its goals with limited human intervention or supervision? Example: cars capable of Level 3 autonomous driving, which can operate without human intervention under certain circumstances, have greater independent execution than traditional cars that require continuous human operation. Following recent literature, we will generally refer to systems exhibiting high degrees of agenticness as agentic AI systems, to emphasize that agenticness as we use it here is a property rather than a category classification, though we will sometimes use agents as it is the prevailing term of art in some contexts. This work will focus on the range of effects and best practices that may become relevant as systems' agenticness increases. We emphasize that agenticness is a distinct concept from consciousness, moral patienthood, or self-motivation, and distinguish a system's degree of agenticness from its anthropomorphism. Indeed, we will generally conceptualize agentic AI systems as operating in pursuit of goals defined by humans and in environments determined by humans, and often in cooperation with human teammates, rather than fully autonomous systems that set their own goals. Agenticness as we define it is also not tied to physicality, i.e., many digital systems are more agentic in the sense above than most robots, but certain kinds of independent execution that have physical consequences, e.g. in a driverless car, can increase the risks and opportunities of agenticness in particular applications. Lastly, agenticness is conceptually distinct from an AI system's level of performance on a given task or the generality of its capabilities, though improvements in performance and generality may unlock the ability of a system to act as an agent in certain contexts. 2.2 The human parties in the AI agent lifecycle. We provide a simplified overview of the agentic AI lifecycle, though there are many different configurations of these roles in the AI industry, and we hope further taxonomies emerge. In our taxonomy, the three primary parties that may influence an AI agent's operations are the model developer, the system deployer, and the user. The model developer is the party that develops the AI model that powers the agentic system, and thus broadly sets the capabilities and behaviors according to which the larger system operates. The system deployer is the party that builds and operates the larger system built on top of a model, including by making calls to the developed model, such as by providing a system prompt, routing those calls to tools with which the agent can take actions, and providing users an interface through which they interact with the agent. The system deployer may also tailor the AI system to a specific use case and thus may frequently have more domain-specific knowledge than the model developer or even the user. Finally, the agent's user is the party that employs the specific instance of the agentic AI system by initiating it and providing it with the instance-specific goals it should pursue. The user may be able to most directly oversee certain behaviors of the agentic system through its operation, during which it can also interact with third parties, e.g. other humans or the providers of APIs with which the agent can interact. Sometimes, the same entity will fulfill multiple roles, such as the same company both developing a model and then deploying it via an API, making them both the model developer and one of the system deployers. Other times, multiple entities will share a role, such as when one company trains a model and a second company fine-tunes it for their application, making them share the responsibilities of a model developer. We will also occasionally mention other relevant actors, including the compute provider, which operates the chips and other infrastructure on which agentic AI systems run, and third parties which interact with the user-initiated AI system. We illustrate with the specific example of a scheduling assistant built on OpenAI's Assistance API. OpenAI developed the GPT-4 model, making it the model developer. OpenAI deployed the infrastructure, including serving the model and connecting it to tools such as a code execution environment, and the application developer builds an app on top of it, e.g. by building a user interface, choosing a system prompt, and supplying an email template for the system to use when sending invites, meaning they both share the role of system deployer. Finally, a customer initiates a session with the scheduling assistant and specifies which goals, e.g. scheduling requirements, they'd like the system to satisfy, making them the user.